The section of the TeX82 listing is part 20, starting in section 456, page 158 on your copies. The important thing to understand here is what kind of files TeX uses in order to get all the information it needs about fonts. And these are called TFM files, TeX font metric files, and they are used not only by TeX but by other system programs. And the design was intended, to make it a compact way to communicate lots of information. These were designed by Lyle Ramshaw, who's sitting here in the audience today. And so he's going to be bored by this hour, but he can also correct me in case I make mistakes. So a TFM file consists of a long string of 8-bit bytes. When we send you a TFM file, we found that the easiest way to do it so that nobody could get confused by this is by sending these bytes in decimal with spaces between them, so that the bytes would say 0 space 255 space or whatever in decimal. Everybody has been able to read those kinds of files. Then there's a 2 or 3 line program in Fortran or something which will convert those into whatever your local conventions are for files that are made out of 8-bit bytes. Packed file of 8-bit bytes, but that seems to vary greatly between systems. As far as TeX is concerned, it just calls it a byte file, which means a packed file of 8-bit, and 8 bits are numbers between 0 and 255, it has to be 0 to 255, not minus 128 to plus 127. When we refer to something from the byte file, we're going to get the next byte from it, and it's got to be a number between 0 and 255. You have to do something to make sure that assumption is valid, but that's the only assumption we make about byte files. Now, actually, you could also consider it as 32-bit words, because the number of bytes in the file is always a multiple of 4. And we always read it, and we always read them, almost always read them 4 bytes at a time. It's only at the beginning when we read them 2 bytes at a time. And so if you wanted to, you could imagine it as consisting of these words. But but for TeX purposes, it was better to stick to a smaller number of file types if possible. So TeX has alpha files, byte files, and word files. We needed those 3 anyway. Didn't want to go to a 4th one, which was made out of 32-bit words. From TFM file, let's think of it as bytes, but 4 bytes to a word. So I'm going to draw my lines here indicating 4 bytes, and I'm going to consider that the bytes are left to right located in a word. So byte 0, the file, byte 1, byte 2, byte 3, and so on. This is what Lyle calls big endian order, where the big end, is that right? You nodded your head this way.
It's called the big endian order, but I didn't invent the term. Dan Cohen of ISI invented the term in a very amusing essay about byte order inside of words.
Oh, okay. Because they go in different ways, and that's why we transmit them as bytes this way. But I'm going to represent them on the board, assuming that this is your first byte, second byte, third byte, fourth byte. That's just a convention for the way I write them. Now the first part of the file is 6 words long, so it's always fixed, and it tells you how big the rest of the file is. It has 12 half words in it, 12 16-bit integers that are composed of the first byte times 256 plus the second byte. That's the big endian order there. So this is the length, and we got a whole bunch of these things. They're all described in Module 457. I'll just read them to you so you get the feeling of it. First comes the length of the entire file in words. The length of the header data. So the rest is the next parts of the file. There's the header, and then there's the char info. Let me try to do it from memory, and then I can correct it afterwards. This will be more fun for me. It'd be confusing for you if I get it wrong, but let's hope I get it right. Then comes the width. Then comes the height. Then comes the depth. Then comes the italic corrections. Then comes the ligature kern instructions. Then comes, plan ahead here, then come the kerns, and then come the extensible characters, and finally the parameters. That's all. Just made it. Now, did I get it right? Wow. Okay, kerns, yeah. Now, so start out length of the file, then the length of the header part. Then the next two half words here are the beginning character and ending character of the font. And characters don't have to be consecutive inside. There's another way to indicate gaps inside, but this is more efficient if we can. If you don't have two characters in the font, one of which is number 0 and the other is which 255, because then we have more space in here. The char info starts at BC and ends at EC. And so there will be zeros in here for missing characters, but the fewer those are, the fewer words of char info you need. Char info is packed, as I'll describe later, giving for each character in the font information about its actual width, height, depth, and italic. Those pieces of information are indirect pointers to the width, height, depth, and italic correction parts of the format file that come next. So char info follows here. Then you specify the number of widths, the number of heights, the number of depths, the number of italic corrections, the length of your the number of commands you have of ligatures, kerns, the number of kerns, the number of extension parts, the number of parameters. So this first part just gives the length of all those, and there's a formula that has to be satisfied that the length of the file has to be 6 plus length of the header plus and so on. That has to be checked. And so you'll know something is wrong if that equation doesn't work out correctly. Now, the beginning character and ending character are supposed to satisfy the relation BC minus 1 less than or equal EC less than or equal 255 inside of TeX82. I'm not saying that BC has to be less than or equal EC. You could have beginning character equals 1 and ending character equals 0. That's the empty font. It's not a particularly interesting font, but I just made sure that it would be legal because the history of mathematics indicated that it was useful to have 0 around, and so sometimes a person might want to be able to input a null font.
Does BC minus 1 really have to be
Greater than or equal 0? I believe so.
What happens if BC is 0?
No, you're right. BC just has to be greater than or equal 0. Sorry. Yeah, excuse me. And that's all I said too in that section. Now the definition of font metric data not only is in this section, but it's also in the other handout that you have called TeXware, and the program in there called TF2PL is the I believe it starts at page 201. It's the second program in the book. It jumps from page 110 to page 201. TF2PL contains a separate description of just copied out of TeX of these fonts. Again, it's reproduced there, but with a slight more generality, because this is intended also for processors that are a little more general than TeX. And so there will be a comment in that section that's not in the TeX manual. If you look at Module 8 of TF2PL, it'll say, an exception to these rules is planned for Oriental fonts, which will be identified by the condition EC equals 256. We're planning to say that if EC is 256, then we're going to do something special in extension of TeX. Well, I'll say something about that plan. The saving thing about Oriental characters like Japanese or Chinese is that they don't have that many different widths, heights, and depths. In fact, they're almost always the same. They have lots and lots of different shapes of characters, but only a few widths, heights, and depths. So inside of TeX, we would represent those as a character code, first of all, that tells what its width, height, and depth is, and then we would have another thing after it, 16 bits, that tells exactly what glyph it is in the font. By looking for a font that has EC equal 256, TeX in such an extension would know to look for a glyph code besides, to figure out what the actual character is. But the first part of it would be treated just as usual by TeX to figure out the width, heights, and depth. So the different widths, heights, and depths would be described in the ordinary way. Okay, well, that's something that we would then I think we were going to say character 256 would maybe refer to would represent all of the other ones or something like that. There's no large proposal worked out. I just wanted to make sure that this kind of thing would be easy to graft in without much difficulty. Okay. Now, inside of these char info parts, we have the highly compressed data, which makes it possible to do this most of the time. The rest of this, these tables are also going to be fairly short. In fact, well, we can find out how big these files are, I suppose. Let me just type something here so that I can. Let me see. I'm not going to be doing anything real interesting, so you don't have to see it yourself. But if you want to, we could switch over to the computer now for just to test it out. Elaine, can you dim the house lights now and go to the computer terminal and see if we can get anything here? I'm going to try cmr10.tfm on TeXsys and type it out in octal just to see see how long it is. Let's see. Can anybody see? Now this is the beginning of the file. You see that header information appearing in the first 6 words. Can you see it? No? Yeah. They'd like to see the computer screen. Is that connected? Ah. Okay. Gee, what a dreadful thing if you have to watch me all the time. I can't stand to look at mirrors now. So this is the beginning. You see the length of the file in words is 215 octal. No, wait a minute. We got to be careful because these are 36-bit words and they're shifted left. So what is that really? 00215. Now let's see. That's 3, 6, 9, 12, 15 bits. So we need 16 bits. So that'll really be 32 octal, which is 4 times 64, 256, 24 more, 26 more, 256 and 26, 282, something like that, 282 words. So typically we're running between 250 and 300 words for the whole TFM file. You see the next part of the file coming through there. This would be your char info words for this Roman font after the header. The header contains the name of the font. It'll say Computer Modern or something like that, and TeX pretty much ignores that. But then the character info parts, most of these are 0. That's when the height and depth, the depth is 0, for example, on most of these characters. And the bulk of the information is taken by the char info table, and at the end we're going to get things where there are more bits on probably, and that's when we're getting into the height, the actual width data and height data. But it looks like most binary dump files. Okay. So back to the house lights on again then. It's packed, highly condensed, and so we have the TF to PL program available to print that in symbolic form, and we'll take a look at what it prints from that binary data in a minute. Now, the char info words are packed into, they have 4 bytes to them. The first byte, second byte, third byte, and fourth byte. I guess the 0th, the first, and second. This one is width, and it's a pointer into the width table. If the width is 0, however, this means the character is not there. Just the condition width equals 0 is necessary and sufficient as far as TeX is concerned, saying don't put it in the DVI font, and give an error message if the user wants to be told about such errors. So it's an 8-bit pointer. We could handle almost all cases. However, if somebody has 256 non-zero widths and 256 characters in the font, then we couldn't handle them all, because we only have 0 is reserved for a flag to indicate not present. The next one, height and depth, is packed 4 bits for height and 4 bits for depth, which means that we're only allowing 16 different heights, 16 different depths. Furthermore, the first width is 0, the first height is 0, the first depth is 0, first italic correction is 0. This is a convention also that we can help to check that we've got a TFM file. And, well, that doesn't really hurt you, because you usually want at least one character that has height 0 or depth 0, so you're not paying. But now, so if you have a font that has more than 16 different heights in it, the program will round to the closest ones that it had. It'll take all the heights that are there, and it'll pick 16 of them so that the maximum error is as small as possible. That's of little consolation, however, if your height represents the thickness of a rule of a square root sign. So we're careful to design our symbols font so that whenever we have a square root sign, it's not going to be in a font that's heights are getting rounded. They're going to be exact heights given. But typically this is plenty, and we only have that many bits, so that's it. So 4 bits for height, 4 bits for depth are packed in there. Italic correction and tag are here, but this is 6-bit, so this is 8 bits wide, 4, 4. This is 6 and 2. Italic correction, and we have 66 bits, so we can have 64 different italic corrections in the file. If I'm not, if I calculate each italic correction by a tricky math formula, then I tend to get 65 or 66 of them in a typical italic font of 128 characters. But rounding doesn't really bother me on on italic corrections, the I won't see the difference of a percentage point of a point. So we got that thing. Then the tag field, which has 4 values, and then there's the remainder field, which is sort of like a parameter to the tag, 8 bits. Now the tag has 4 values, and 0, 1, 2, and 3. 0 is the vanilla case, the normal case, and almost all characters have a tag of 0. Tag of 1 is lig. It says a ligature kern program is there. And in that case, the remainder is a pointer into the ligature kern commands, and we start looking there to see what about ligatures and kerns. We'll talk a little bit more about that in a minute. Type 2 is where we have a character list. And this means there's a next larger character in some list of characters. For example, left parenthesis might be linked together, and so we can get to the next larger one and the remainder is a pointer to the character that's next larger in the sequence, and that can point to still another one, and so on. So we can find we can have lists of characters. And the last one is the third case is for an extensible character. And in that case, the remainder field is a pointer into the extensible recipes for making up extensible characters. Well, I can explain extensible recipes right now. Extensible recipes have 4 parts: top, middle, bottom, and repeatable part. And these are the names of 4 characters in the font, or they might be 0. In these 3 cases, they might be 0, indicating that the thing isn't present. So we make up repeatable characters in that way. For example, a left curly brace has all 4 things present. The repeatable part is this here. It gets repeated as many times as you need, the same number of times above and below. The middle part, of course, is this, the top part this, the bottom part that. 4 different characters, and TeX will take top, any number, n of these, then middle, then n again of these, and the bottom. If the middle is empty, that would be indicated by 0 here. That would be a character like a left parenthesis, has just a top, a bottom, and a repeater part. Font designer to make a good font, the font designer should make the set of all different widths that you can get be the same for all of his delimiters. You shouldn't, for example, so that if you have a left parenthesis with the repeater part 6 points, then your repeater part for braces should be 3 points each, so that you'll have the same sequence of length. Because when TeX is matching, suppose somebody for some reason wanted a left parenthesis and a right brace, it would be funny if the right brace would be a different size from the left parenthesis, just because the set of different available heights is different for the two. You'd like to make them consistent. So you design it so that the set of different things that can be made up has the same dimensions. Anyway, you take a symbol like vertical line that doesn't have top, middle, or bottom. It's all repeater parts. And one of these floor brackets has bottom but no top, and so on. I haven't seen one yet that has a middle and nothing else, but you can imagine all those combinations. The repeater part is always there, even if it's 0. That would mean that 0 is your repeater character. But if it's an extensible character, this is used in certain parts of TeX math mode to see if this character is an extensible character, and then it would see if the tag is 3. Now, what about the ligature kern programs? I think we've covered everything about this except parameters and ligature kern commands, because widths, heights, depths, these are just the different depths. I got to mention though that these are given in in certain units because they represent physical dimensions, so we ought to talk about those units. In the header part, there's two important words as far as TeX is concerned, and I forget which comes first and which comes second, but first is the checksum, and next is the design size. So we got to talk about those two things. Checksum first. That's a number that's supposed to be change if TeX important information is different. If, for example, somebody uses TeX to produce a DVI file in January, and then you use that DVI file to print in February, the checksum that TeX found in its TFM file that used in January should agree with the checksum that's being used in February to print the font. Otherwise, there's been an incompatibility. Okay, and so this checksum is computed by Metafont. If the checksum is 0, it doesn't no test is made. But otherwise, the user is warned that something has happened to the font in the meantime, so that the assumptions that TeX made generating the file are not necessarily valid anymore, and we can't maybe print it correctly. So beware. That's what the checksum is for. The design size is the size that's sort of normal for this font that the designer had in mind. But it's kind of an arbitrary thing. It's just what all the other units are expressed in terms of. So all the widths are expressed as multiples of the design size. All the heights, depths, italic corrections, kerns, and parameters, except one parameter is pure number, but all the other parameters are expressed as multiples of the design size. The design size doesn't necessarily have to reflect any universal truth or something. But if you say that that your design size is 10 points, this is given in units of points. Then if somebody just calls for this font without saying at a certain other size, then he gets it at 10 points. The design size is sort of the default at size. So a person in writing in TeX will say font 10 equals CMR 10, and its design size happens to be 10, and the design size of CMR 9 happens to be 9. But if he says CMR 10 at 15 point, then TeX just reads in the same TFM file but pretends that 15 was the design size here. And so everything is in a multiple of the design size, so everything gets multiplied by 15 instead. Now these widths are actually given as what the documentation calls fixed words, and fixed words are fixed point things that have 20 bits to the right of the decimal point. So there's 20 bits to the right of the decimal point, and therefore 12 to the left of the decimal point. Okay. Now the fixed words, however, should not actually use all of this precision to the left of the decimal point. TeX is only going to allow them to use 8 bits to the left of the decimal point, or is it 4? 4 bits, yeah. Only 4 of those should actually be used. So we're not saying, so nobody's supposed to have a width more than 16 times the design size. So for example, if you really want to have something more than 16 m's, the design size we might call an m typically is 1/4 1 m. If somebody really wants to have a character that's more than 16 m's in some direction or other, he should say that his design size is larger. Okay. And the reason is that then TeX can do the conversion, multiplying by the design size with single precision without a lot of time, and it saves these internal calculations. So so these are given as fixed words. So the first byte will either be 0 or 255. A negative is given in 2's complement notation. So the first byte has to be 0 or 255 in all the widths, heights, depths, parameters. Okay, now to ligature kern commands. Here's where we got another highly efficient way to pack logic into bits. And ligature kern command table is there's a big table of instructions, possibly big, but possibly empty. If the tag bit was 1, that would say the remainder is an index into this table as to where we start. And there's 4-byte commands in the table, and you execute this command, and if it didn't find something, then you go on to the next one. Now the commands have 4 parts, and the first one is called the stop byte, or the stop bit. This one is called the op, I think. This one is called the character, and this one is called the op, and this one is called the remainder, or the operand or something. I don't have a specific name for it. Call it remainder. And the command has the following. Right now we're using 1 bit for stop, 1 bit for op, 8 bits for character, and 8 bits for remainder. So people like Pierre Mackay have been eyeing these extra 14 bits with great interest, because they want to do things for Arabic and other languages where they would like to go beyond 256 character limit. Right now we're just using the high order bit in the stop byte and the op byte. The commands means this: look at the next character following the present one, and does it match this one? If not, go on to the next instruction, or stop, depending on whether the stop bit is there. So the first thing is look for a match on the character after it, and if you didn't find it, then you stop if this stop bit is on. Otherwise you go on and sequentially until you either find a match or you find a stop bit. Now, if you did find a match, then the op bit tells you it's either a ligature or a kern. If it's a kern, then you'd look at the remainder part, and that's an index into this kern table here. It tells you how much the kern is. If it's a ligature, the remainder tells you replace your present character and the following character by this one, and then start the whole process over again. Pretend that was the character that was input, and go through and see if that character in turn has a ligature tag. And if so, it will refer you to its program to continue on. So see what happens then. F, for example, in the typical American version of ligatures, F has a ligature program that says, if you're followed by an F, then replace this by FF character as a ligature, and go on. If you're followed by an I, replace it by FI, and same for L, similar. Then FF itself, FF ligature, if followed by an I, then replace that by FFI. F would also be also often followed by kerns. For example, F followed by an exclamation point. You'd want to put some extra space between F and the exclamation point so that they don't run into each other. Quote marks, same way. Okay, so that's the idea of these ligature kern instructions and command. And TeX will interpret this in several parts of the program. So let's now see what the TF2PL program does with this. And so let's have the lights off and go back to the computer and see if this works. It's still up. TF2PL. TF2PL is a program that is one of these TeXware programs that you've got. And it asked me for this TFM file, and I'll just use the CMR10 TFM that on TeXsys that we were just looking at in binary on this. And I'll print out CMR10.pl, and this is the program that you have a listing of doing it. It prints out the character codes that it has processed as it's doing it. Okay, so now we should be able to look at CMR2.